Hey guys, today we'll be analyzing the toggle mechanism. Here's the simulation for this mechanism if you're really interested. Like I said before, visualizing is the heart of all kinds of analysis. You need to know how the individual links move accordingly with the crank's rotation. Let's go for the velocity polygon. There's an anti-clockwise rotation of the crank OC, and so here comes the tangential velocity from fixed points O and A. As you can see, power from this crank is transferred to the next crank through the rod BC, which in turn causes the piston to move to and fro. And we are sure about the surface over which the piston D is gonna slide. Now BC has a tangential velocity towards the right. We just draw a line as we don't know the magnitude yet. There are links having more than one relationship with the other links, so they won't be available for us explicitly. As we move through the mechanism, we get in the crank AB, which also has a tangential velocity, as it's spinning with some angular velocity. It looks like there's an intersection. That should be B because that connects the crank OC to the crank AB. Now let's move to the link BD. Its tangential velocity is perpendicular to the link. That line extended from B in the velocity polygon intersects the surface at D. Measuring the lengths and scaling them up gives you the relative velocities between those 2 points. Okay, next we move on to the acceleration diagram. Always start with the given data. We have the radial acceleration from OC, and we also have the surface. If you want, you can also draw the tangential acceleration for OC. Then we have the radial acceleration from BC. We also have the tangential acceleration from BC. There's another crank AB, which has a centripetal acceleration from B to A. B to A. It's really hard to guess the lengths of those lines. They are somewhat exaggerated here. Okay, this should be the crank's radial acceleration, and it has tangential. We make use of the tangential components for all the other links except the driver because those things are ran by the driver. And as you can see in the simulation, these links always have some kind of angular motion, and they accelerate and decelerate often. So there's a tangential acceleration. And there's an intersection. These intersecting lines are drawn from C and A, and there's only one joint connecting them, and that's definitely B. Don't worry about those primes on the top, I'm just using that to differentiate these from the other vectors. Now this link BD has a radial component which goes like that, and a tangential component that goes like that. There we see an intersection. That should be D because it's the only link moving in the horizontal direction. On connecting the respective points in our diagram, you'll get the relative acceleration between those two joints. Thank you.